So I want to start today's lecture with a little bit of a demonstration that's outlined in the text. We know so far we've treated friction only as a constant force that's given to you. But if I were to take my index finger and set it down here on the table, I'm going to have some friction. I can tell this because it takes a force to slide that finger across with my little pinky. However, that force is not constant. If I touch down very lightly, it's very easy for me to push it across with my other finger. By contrast, if I push down really hard, it's very difficult for me to even get it started, and once it's started, it's still difficult to slide it across the table. You can try that for yourself. So what we find is that somehow or another, the force of friction has to depend on how hard the object is being pushed into the table. So here's an illustration of what we just demonstrated, pushing down and showing that we get more friction the harder we push down. If we were to do that very carefully and plot the data, what we find first off is that the friction is proportional to the normal force. The harder I push down, or more importantly, the harder the surface pushes back at me, the stronger the normal force, the more kinetic friction, the more sliding friction I get. And the data points all lie fairly nicely along the line, so that if I fit them, I get this straight line with a slope mu equal to 0.21. So I can then write that into an equation. This is just the equation that says that the force of friction, kinetic or sliding friction, is equal to this coefficient mu times the normal force. In this particular case, the coefficient mu that I found was 0.21, and I put the little k here to tell me it's kinetic, or that it's the friction I have when I'm actually sliding. Now the next issue is to talk about, what about the friction when I'm at rest? Well, it turns out we can use a similar equation. It says the force of static friction is equal to mu static times the normal force. So let's take an example of a calculator. Suppose my little blue calculator has a mass of 50 grams, which I can get into kilograms. That is 1 kilogram for every 1,000 grams, and this gives me 0.050 kilograms. Then I want to know the normal force. Well, it's sitting on a table. Gravity pulls down with a force of mg. Normal force pushes up, making a free body diagram. I've got a normal force, I've got gravity, and from Newton's second law, I know that normal minus gravity equals ma. It's not moving up or down, so the acceleration in the y direction is 0. The normal force equals mg, which is just 0.050 kilograms times approximately 10 meters per second squared, which gives me 0.50 newtons. If we then assume that the coefficient of static friction is approximately 0.20, then the frictional force will be 0.20 times 0.50 newtons, and that gives me 0.10 newtons. So I should have a frictional force of 0.10 newtons. And of course, that will give me an acceleration. We know that frictional force is apparently the only force in that x direction. So F equals ma, and the acceleration is force divided by mass, 0.10 newtons divided by 0.05 kilograms. That would give me 2.0 meters per second squared. So So let's consider the reasonableness of this. We've just said that we've got a force of friction of 0.10 newtons, which will give us an acceleration of 2 meters per second squared. Let's look at the situation and think about whether or not it makes sense. So we've just determined that this calculator has a mass of approximately 50 grams, which means it has a weight of about half a newton, and that half a newton weight is matched by approximately a 1/2 newton normal force pushing it up. Because we estimated the coefficient of static friction to be about 0.2, we would expect to have a frictional force of about 0.1 pushing on this calculator. So then we ask the question, which direction is it pushing? And of course, a 0.1 newton force on a 50-gram object should cause it to accelerate at about 2 meters per second squared. I don't see it accelerating, do you? I really don't see that accelerating at all. So what that tells us is that maybe our calculation is not complete. In fact, static friction is not always a certain value. It's whatever value is necessary up to a certain maximum value. So 0.1 newtons is the maximum amount of force we could have on this. If I don't push on it at all, it has no frictional force. If I push on it very lightly, say with a force of 0.01 newtons, then friction will push back with the same force of 0.01 newtons to keep it from moving. If I push with 0.03 newtons, friction pushes back with the same 0.03 newtons to keep it from moving. And only when I push with 0.1 newtons do I start to get it moving. That's where I reach the maximum, is right on the edge of sliding and not sliding.